In this second half of solving with proportions, I want to do two examples that are pretty challenging and they actually are set up similar ways. So they're good to group together in this video. So here is the first example. It says, Sam can complete a job in 3 hours, but Frank, who is new, needs 7 hours to complete the same job. How long will the job take if Sam and Frank work together? So we're assuming that Sam can do the job 3 hours by himself. Frank, it would take 7 hours by himself. So how long would it take if they both work together? Now, you want to be careful here. It's not going to be an average or anything like that because they're working at totally different speeds here, right? Um, if Sam can complete the job in 3 hours and Frank is going to, let's say, be helping him, then they should be able to finish that job in less than 3 hours, right? Like it's not going to add more time to Sam's hours to complete the job if they're working together. It should be faster. So I'm guessing it's going to be something under 3 hours because even if Frank is slow, he's still helping on the job, right? So the way we do this is as follows, and this is kind of a little bit of a trick or a technique to use for this style problem. Notice, first of all, that we're talking about hours here. So we're going to relate everything to 1 hour. So for instance, for Frank, in 1 hour, he can complete 1/3 of the job. Now, how did I get that? Because it takes him 3 hours to complete the job. So if I'm doing 1 hour, it's 1/3. So I'm using a ratio here. Oh, sorry, that's for Sam. Whoopsies, Sam. For Frank, in 1 hour, he can complete 1/7 of the job, right? It takes him 7 hours to do the job. So in 1 hour, he could get 1/7 of the work done. All I'm doing is I'm relating these both to the same units. So they're both hours. So let's break it down to how much each person can do in 1 hour. So Sam can do 1/3 of the job in an hour. Frank could only do 1/7 of the job in an hour. And then we're going to let X equal is it's going to be the time in hours it takes Frank and Sam to complete the job together. Now that was our question, right? So our goal here, how long will it take if Sam and Frank work together? Remember, your goal should lead you to your variable. So if you're like, well, how did you figure that out? It's because I'm using the goal here. The goal is what we're trying to figure out. I don't know the answer, so it's got to be X, right? So we're going to let X be that time that it takes them to complete the job together. So let's relate this all to 1 hour then. So in 1 hour, together, they can complete 1x of the job. All right, so the last thing we need to do here is we need to create an equation. And the way the equation is going to work is as follows. So we're going to see, so basically we're going to add in Sam's part of the work plus Frank's part. And that should equal the together part, right? What they do together. So here, let's see, Sam's part we said was 1/3. Frank's part is 1/7. And together it's going to be 1/x. And this is all in terms of 1 hour. So it's all being consistent here. And now I'm going to have to go to the back page here so we can actually solve this. All right, so I have 1/3 plus 1/7 is equal to 1/x. Now I have to use LCD here because I don't just have one ratio equals one ratio. So I cannot cross multiply. Here, I'm going to have to use an LCD. So 3 times 7 is 21, and then I also have an x here. So I'm going to multiply everything by 21x. And in the first case, 21 over 3 is going to be 7. Here, 21 over 7 is going to be 3. And then the last case, the x's cancel. So in the first case, I have 7 times 1 is 7 with the x. 3 times 1 is 3 with the x. And here, 21 times 1 is just 21. So I end up with 10x is equal to 21. Divide both sides by 10, and I have 21 over 10, which is the same thing as 2.1. Now remember, what was x? X was the time that it takes for them to complete the job together. And the time we're talking about here is hours. So this would be 2.1 hours. So together, they can complete the job in 2.1 hours. Again, assuming that they're keeping that same pace. Obviously, in the real world, that could change a little bit if their pace changes and so on. But if they're keeping the same pace as they currently are, where it takes Sam 3 hours and it takes Frank 7 hours, if they work together, they should be able to get the job done in 2.1 hours. Now, you can go ahead and you can check this. Again, I'll let you guys try the check at home. If you plug this in, it does work. So it would plug in and it would work correctly here. And it also makes sense, right? So this is one where the biggest mistake students do is they'll take the 2 hours and they'll just average them. And they'll say, oh, well, it would take them 5 hours to work together. But that doesn't make sense because Sam can do it by themselves in 3 hours. So it's not going to add 2 hours on to Sam's time to have help, right? It has to be something less than that. So 2.1 does make sense here. But this is the strategy that we can use for this style problem. Now, the next example is going to be similar. Again, it's a tough one where it's not a very natural feeling strategy. I don't think it's one that you kind of have to see and learn. So this one says that car A travels 180 miles in the same time that car B travels 120 miles. So they're both traveling the same amount of time, but car A is obviously traveling a lot further. If car A's speed is 20 miles per hour faster than car B's speed, find the speed of the two cars. So there's my goal here is we're trying to find the speed of the two cars. So I have to find two different speeds here, right? In this case. So I need the, let's see. So this is our goal. So I need car A's speed. Oops. And I need car B's speed. Now we're not going to use two variables here. We're going to just stick with one. And if I read through, I see that car A's speed is 20 miles per hour faster than car B. So for car A, it is 20 miles per hour faster than car B. So I have extra information about car A. So that means I'm going to let X be car B's speed, and then faster would mean that I'm adding here, right? Because if you think about speeds, if one car is going 5 miles an hour and the other is going faster, it would be going like 10 miles an hour or 20 miles an hour, right? It'd be going up. So for faster, we'll be adding there. So 20 plus whatever the speed for B is. So I have my basic setup here. Now, the other thing I need to use here, and this is something, again, you've seen it before, but you may have forgotten it. So we do need that distance formula here. So distance equals rate times time. Anytime you see distances and speeds and time, you kind of want to think of this formula, but it may not be your first guess to go right there. So this is the formula that we're going to use here. So for car A, what do I know? So car A, their distance was 180 miles. Their speed, now speed also is R. R is rate, which also means speed. We said was 20 plus X. And I don't know the time, but I do know that it's the same for car B. So I don't actually know this, but I do know that these are the same. Then for car B, our rate is X and our distance is only 120 miles. Now, what I want you guys to notice, which is the key thing here, and again, these are the two tricky ones, I think, for this topic, is that this idea that the times being the same is key. So the time for car A being equal to the time for car B is how we're going to get our equation. Now, in the distance formula, right, I have distance is equal to rate times time. So I can rearrange this and solve for time instead. And I can do that by dividing both sides by r. And then I have that the time is equal to the distance over the rate. And that's what I'm going to use here. So my time is equal to the distance over the rate in each case. So for car A, my distance is 180. My rate is 20 plus x. And then for car B, my distance is 120 and my rate is x. Now, in this case, I actually can use the cross-multiplying trick because I have one ratio equals one ratio. So I'm going to multiply this way and this way. So I have 180x is 120 times 20 plus x. And I'm going to have to distribute here. So let's see, I'm going to get 2400 plus 120x. I'm going to subtract that 120x to both sides. So I have 60x is equal to 2400. And dividing by 60, I end up with 40. Now keep in mind, what were we trying to find here? I'm going to go back up to the top here. X was speed, and everything was in miles per hour, right? So car B's speed is the X. So car B is going 40 miles per hour. That was our answer here. But car A, we said, was going 20 miles faster. So it's going to be 20 plus X, which is 20 plus 40. So they must be going 60 miles per hour instead. Now, again, I'm going to let you guys check this at home. This does actually check out. So first of all, if you plug 40 back in, you do get a true statement. So that is key. Check that out. Make sure nothing looks bad there. And then the second thing is this actually does make sense, right? If you think about this here, right, 180 divided by that 60 is going to give you 3, whereas 120 divided by 40 also gives you 3. So they must both be traveling for 3 hours, right? Which makes sense in the same amount of time. So these numbers do work out. And again, they do make our proportion correct here. So these two are definitely the trickiest problems, I think, in this section for proportions. They're not hard, but if you've never seen them before, again, you may not know how to set them up. So when you're seeing a lot of distance and time or speed, think about that distance equals rate times time formula. And in the other case for work hours, that idea of getting it down, well, in that case, it was for hours. So 1 hour base was actually really key. So that is a really helpful technique to use there as well.